Hello, everyone. My name is Dongchen Wang. I'm a postdoc at Caltech. So today I'm going to introduce you the sediment transport module we basically our team developed for the DataX project. So this code was originally started, and the development was originally started by Dr. Gerard Sauté. Then last year I took over and basically finalized the development of this code. So I think right now this code is in the process of final revision. So I think the link I share is basically still under revision. So if you want the final product of this code, probably we still need to wait a little longer. Yeah, I think Mark might tell more information on this. Yeah. So the purpose of developing this semi-transport module is basically to implement sediment transport theory like with great flexibility. So because as you guys have been participating in the application workshop, there are many existing like morphodynamic code, hydrodynamic code. So many of them are complicated to like make changes, especially on the source code level. So this code, this sediment transport module is relatively simple, and basically everything is open sourced and is written in MATLAB language. So a lot of things are simplified. But the disadvantage of this code is that this code is not parallelized. So right now we can only use this sediment transport module to run some of the smaller cases, as you are going to see in this presentation. Okay. So here is the agenda of this talk. Basically, first I'm going to introduce the background of the whole project, and then I'm going to briefly talk about the sediment transport theory we wrote into this sediment transport module, and then because this code is designed for short-term simulation, so we performed like two 14-day events using this code, basically corresponding to two intensive campaign performed by the DataX teams. And then we are going to discuss some upscale strategy to use the short-term modeling result to estimate like 1 year land accretion or even longer land accretion rate, so we can get some long-term prediction power out of it. Yeah, and then I will start to talk about more details of this code. Basically, I'm going to introduce the structure of the sediment transport module. Also, the hands-on session will be basically step by step to introduce how the code is working. So because again, this code is like dealing with the problem like a wax lake delta scale. So you might not able to run the full case like today, but I'm going to provide some files you can use to just to look into how the code works, and you can play with all these files. And if you are interested to use this code to run a full case, probably you will need at least a desktop, and maybe the running will take a few days or even weeks to run. Yeah, so that's just very brief introduction on the agenda today. So the motivation is, of course, to numerically model the land evolution process of the wax lake delta, which is the like one of the core investigation area in the DeltaX project. So basically, I think previously in previous presentations, people have already talked a lot about backgrounds. I will skip the background of here. Then basically, here is like a very high level introduction of what this sediment transport module is. So here shows a very standard morphodynamic model solver procedures. Basically, for any morphodynamic model on the market, basically the model first needs to solve the shallow water equation, which corresponding to the flow dynamics. And then using this flow dynamics variables feed into sediment transport module. Then the sediment transport module solves the transport equation if we want to model the suspended load. Then with the sediment transport equation being solved, we have the entrainment and the settling flux at the of the sediment over the domain. And then using the entrainment and settling flux, we solve the Exner equation, finally get the bed evolution also to update the stratigraphy. So this process is called quasi-steady coupling of the flow and the sediment equations. But in this case, we're going to use the calibrated hydrodynamics model that is like generated using ANUGA. So you already see a lot of ANUGA presentation yesterday. So taking the ANUGA hydrodynamic model result as the flow condition, basically the sediment transport module will not solve the shallow water equation, but directly solve the sediment transport equation and also the Exner equation to obtain the sediment transport load and also the bed evolution, which is basically the land accretion rate. So this is where what this sediment transport module is. So then I will again introduce very quickly introduce the hydrodynamic model result obtained from the ANUGA simulation. So from ANUGA simulation, we have all these variables like water depth, velocity, friction, also the flow flux. So we have all these variable directly basically adapted from the ANUGA result. And this model, the figure on the right basically shows the modeling domain of the ANUGA result I'm using in this workshop. This result was developed by the UT Austin team. So basically, the sediment transport module will take the ANUGA result and crop this shaded area. Basically, we only consider a small domain of this big domain, and we adapt all the like hydrodynamic result in this shaded region and compute the sediment transport in this region. So this is basically the plan. Now, before dive into the detail of the like code of the sediment transport, I'd like first to briefly talk about the theory behind the sediment transport module. So the big question here at Wax Lake, there's a big research question behind the Wax Lake is how the cohesive sediment or the mud particle being transported in this in the rivers, also in the coastal region. There are commonly three hypotheses. The first hypothesis is this mud particle is transported in the form of flocculated particles into like in the form of aggregates. The second hypothesis is like this mud particle is transported as like really ultra fine individual grains, like the grains that is smaller than a few microns. Then there's a third hypothesis is the a more commonly accepted hypothesis. That's the classic theory of mass transport, is the wash load hypothesis. Basically, it says the sediment is transported in a way that it does not interact with the riverbed. It just passes and directly passes the river through the river and being directly delivered to the ocean. So that's sort of three hypotheses. So if you dive into all these three hypotheses, you will find that the main question here is to know what is the particle settling velocity in all these cases. Because if you think about the flocculated particles, they settle at a very fast, at a faster speed than the individual fine grains. And the wash load hypothesis is like basically the sediment does not settle at all because it does not interact with the bed. So here's, for those who are not familiar with the settling velocity, here's a very brief introduction. Basically, for any like individual grains, we can use the force balance. Basically, we put a particle in, for example, in a container and let it settle. Then, because of the force balance between the fluid resistance and the gravity force of the particle, it will eventually reaches a equilibrium condition. That the particle will travel at a constant speed while these two forces balance each other. So if you compute this balance, you'll find that if you have larger grains, basically you have a more material for each grain, and then it's more heavier. And then in the fluid, this particle will settle at a faster speed. If you have a finer grain, of course, the particle will settle at like a smaller speed. So if we plot these two axes onto the diagram here on the right, basically it will collapse into this red line. This red line is called the Stokes law. It is basically a function of sediment diameter and the settling velocity. But in the field observation, it is not entirely true to use the Stokes law to predict the sediment settling velocity. One main issue here is because all these fine sediment, they are not. Sometimes they don't transport it in a way of individual grains, but they actually aggregate together because the finer particles tends to have some organic matter on its surface, and they tend to form this kind of sticky, like flock grains. Once these fine particle they form these larger flock grains, these flocks can have almost the same size as the sand. Basically, if basically increase the increasing of the like aggregates will basically increase the gravitational force of the particle, and hence the flock settling. If you look at the flock settling data, you will not perfectly locate on this red line here. All these flocks are being accelerated, and the measured settling velocity will basically can be a few orders of magnitude faster than the measured data. So the idea of this work is basically to test all these different hypotheses. Then to see how this smart particle settling velocity impacts the land evolution at Wax Lake Delta. Yeah, so here shows more detailed implementation details of how this code is basically written. So these are the two main partial differential equation that the code that this semi-transform module is solving. The first one is Exner equation. So basically, the change of bed is equals to the entrainment flux, which is the EI, and the settling flux, which is DI. And then on the second equation, this code solving is the advection diffusion equation or the transport equation. So the same thing here, we have the entrainment flux, which you can see with two negative sign here. The entrainment flux will increase the concentration, while the settling flux will decrease the concentration in the water column. In these two governing equations, basically there are question on how we should compute the entrainment flux and the settling flux. So this is one of the main motivation that the team decided to write this code, is to have the flexibility to change the formulation of the entrainment flux and the settling flux, also to adapt the different theories easily. The entrainment flux is sort of a mystery in the sediment transport theory. So it is not well defined in a way. So usually people use basically dimensional analysis to calculate the entrainment flux in an empirical way. The common dimensionless number used to calculate the entrainment flux here gives two examples. It's the ratio between the shear velocity and the settling velocity of the sediment, and also the flow number, etc. So here in this code, we implemented the entrainment flux formulation developed by Delu 2020, which gives the form of this way. So you can see it's sort of the empirical fitting of this two dimensionless number and the entrainment flux. Then there's a second thing is the settling flux. So the settling flux is sort of calculated in a pretty standard way here. That is basically the settling velocity times the near bed concentration for each sediment class. So yeah, you can see that the settling velocity, how to determine the settling velocity is really essential in the sediment transport, in the suspended load sediment transport theory. Here, it impacts both entrainment flux and settling flux. So by after all this introduction, we can basically see where this goes. The object of this work is to build a sediment transport model that can capture the sediment transport pattern at Wax Lake Delta, especially the fine sediment transport pattern. And then we're going to test different hypotheses and their impact on the delta land evolution. Finally, we're going to briefly introduce an upscale strategy to how we estimate the 1 year land accretion rate at Wax Lake. So here are three different cases we set up to model the sediment transport at Wax Lake, basically following 3 hypotheses I mentioned before. The first case is to assume the flock, like the fine sediment settles in the form of flock aggregates that basically settles at a faster rate and in train in a slower rate. And the second case is a reference case that basically simply using Stokes' law to calculate the individual grain, mud-grain settling velocity, which will give a slow settling flux for the mud and the fast entrainment flux and the large entrainment flux for the mud. And the third case is the classic cohesive theory that basically does not allow settling of mud in the erosional environment and does not allow the erosion in a settling environment. That's like the classic cohesive sediment like transport theory. So basically in the hands-on session, I'm going to briefly introduce how to modify the code and basically to use all these different theory to set up the case to run all these different cases. Yeah. So this shows an example of the modeled suspended sediment concentration at Wax Lake Delta. So you can see that there's a tidal boundary that is modeled in the ANUGA hydrodynamic result. So you can see there's a very strong influence of the tidal on the suspended sediment concentration. Also, the sediment, by the way, the flow is coming from up of the domain, from the upside into the domain, and this is the delta. Yeah, so you can see that in the high tide condition, basically the flow velocity will slows down, and then there will be a backwater going on in the delta region, and the concentration will be relatively lower. And in the low tide condition, the concentration tends to be higher because there's more turbulence going on. So basically, using the modeling result, we've been using delta X field survey data to validate the sediment transport module. This shows one example how different setting velocity are tested in the sediment transport model, and it is used to compare with the average NG derive the total suspended sediment concentration in order to validate the model result. So in this case, we set up and modeled 2 delta X campaign, as I mentioned before. One is a spring 2021 campaign, and that is corresponds to high flow discharge condition at Wax Lake. And the second campaign is the fall 2021 campaign, and that corresponds to low flow discharge condition. So then basically the idea is to develop a method to use these 2 model results and somehow we combine it together to calculate the 1 year, to estimate the 1 year land accretion rate at Wax Lake region using these 2 modeled event, modeled accretion rate. So the method we used is the called synthetic time series method. So basically we assume that the land accretion rate of 1 year land accretion rate is some linear combination of the high flow land accretion rate and the low flow land accretion rate, and the weight of this weight of these two events is determined by this synthetic time series method. So the synthetic time series method is basically using the time series of the Spring 21 event combined with the Fall 21 event and basically create this cycle that compare with the actual time series. So this weight is the same weight we're going to use in the land accretion rate computation. So you can see if we have more Spring 21 rate, and then we have more high flow condition, and then we have more like a land accretion rate that is corresponding to high flow events. Yeah. So and then basically by adjusting the weight of this high flow and the low flow conditions, we can create this synthetic time series. And then we use this synthetic time series and repeat it for the same period that the observation is taken. So at Wax Lake, there are 30-year observation, flow discharge observation taken at Wax Lake. So basically, we create a 30 cycle of the synthetic time series, and we use it to compare with the actual measured time series here. So you can see this red line is the synthetic time series, and the black line is the measured time series in the past 30 years. Then we used several different measures to compare these two time series. Here shows an example. We compare, for example, the mean flow discharge. We also compute the L2 norm of these two time series. And we also use dynamic time wrapping to compare the similarity of this time series. So you can see that using all these different measures to compare the synthetic time series and the measured time series in past 30 years, we obtain the weight. We obtain the optimal weight, and that the high flow condition should have the weight of 27%, and the low flow low flow part should have 73% in the like upscale process. And then basically what we did is simply weighted sum of the spring of the fall land accretion result and the spring land accretion result. So you can see the upper plot is the low flow result. We time it by 73%, and the lower image is the high flow land accretion modeling result. We time it by 27%. Then we weighted sum them together. We have the final product of estimated 1 year land accretion at Wax Lake. Yeah, so this basically is the whole like what the entire sediment transfer module does. Now maybe we can move to the hands-on session. So this shows shows the basic structure of the sediment transport module. So yeah, if you take a look at the Google Doc.
Dongchen, can you hear me?
Hey, Dongchen,
Yeah.
can you hear us?
Yeah.
There
Yeah, I
are
can hear you.
questions in the chat.
Okay.
Can you address those before the hands-on portion? So
Oh,
the first one is maybe a question for you, Juan and Ariel, is what is the main difference between the MATLAB sediment transport model and the Rado?
Okay. So MATLAB transport model solves the Exner equation, and also it solves the advection diffusion equation. So okay, so the Dorado is a particle tracking solver. So it's different solver first. The MATLAB model is a finite volume solver of the transport equation. So it solves for the land changes, while Dorado it mainly solves for example the trapping efficiency of this particle at each location. Yeah, so Dorado does not give the land accretion rate, like basically. If I understand correctly, the Dorado does not give the land accretion rate following the hydrodynamic condition, right?
That's correct. Yeah.
Yes.
Yeah. So yeah, and this sediment transport model is more like a standard way to solve sediment transport theory, and that will give the exact land accretion rate in terms of for example, meter per year, something like that. Yeah. Also, in a full morphodynamic model, that the land will keep changing, and the land change will have feedback on the flow condition. So land change will then change the flow condition, and the flow condition will then further change the land evolution. So it's more like a two-way feedback between land and flow. So this is another difference. Is Dorado does not have this two-way impact on the hydrodynamic model. Yeah.
Thank you. And then there are 4 more questions in the chat. I don't know if you can see it, Dongchen.
Yeah.
First one is, how are you specifying a spectrum of flock sizes typically found in riverine suspended sediment load in the model?
How do you specify? Yeah. So yeah, it's a good question. So basically, the flock size. There are several ways to determine the flock size, right? So the first way is to there are some people do that is to directly observe it in the field, and take a camera there and take some sample and try to observe the field flock size on the field. Then the method we are using here is it's an indirect way. So basically, the field team brings the equipment called the list. So basically, they measure the grain size, measure the in situ grain size in the river. Then they get a vertical profile of the in situ grain size in the water column. Then the water sample will also be taken at the same location, and those water sample will be brought back to the lab, and then the grain, all these grains will be chemically processed, and all those flocks will be flock aggregates will be break in this process. And then basically what we did is we measure these individual grain sizes. Then we use these two data, these two distribution. We basically calculate all this information about the flocks. For example, we can assume a Rouse profile. If we have the grain size distribution in the vertical column, we can estimate, we can make a hypothesis of a Rouse profile in the water, and then we inverse calculate the settling velocity of the flock, and we can also inverse estimate the flock size using the lab, the difference between the lab data and the in situ measure list data. Yeah, so there are many ways to do this, and this is a long. We have a long discussion on this. Yeah, if you're interested, please send me a message. I can explain that in more details later. Yeah. Okay, the second question is how are the organic chemistry and the turbulence affecting the evolution flock size if different sizes are considered? What we found that is that for all these different grain size classes, the flock tends to have some kind of like a constant like a it's not so if you yeah, let me show you the data here. Yeah. So if you look at the data here, you can see that regardless the flock, like what kind of particle form in the flock, it looks like the flock tends to have a setting velocity that is around 0.3 millimeter per second. So here. So it is the wax lake data sort of sitting around this line here for regardless what is the individual grain sizes. So you can see basically we just use this constant velocity to represent the flock setting velocity. Basically we assume that all the flock will behave, although they have different sizes, although they changes, but statistically they will behave around this value. Then we can just assume a constant value for all the flock sizes or all the grain sizes. And this flock we observed in the field. You can see here. This is a lab experiment example, but in the field it's something similar. That the flock has the size of maybe 1 to 200 micron, if I remember correctly. So it's very similar to fine or medium sand grain size. Yeah, that's kind of the flock size observed. The third question is how do you assign flock distribution for native soil in the delta? Yeah, so flock distribution. Basically, there are some bad sample, like a bad grain size sample. I have, so I'm going to show it in the later part of this in presentation. So yeah, so, I don't really use flock distribution, but I mainly use the MAD distribution, so the fraction of MAD. Then in the model, basically, I have two classes: one class for the mud, one class for the sand. So I use the measure the mud fraction as input in the model.
In my case, was like just assuming.
Okay.
Yes.
What value? The fourth question is what value did you specify for the erodibility? Tau s. Okay. So in this case, again, because we're using so we're not using the classic sediment transport theory to model the mud erosion here. Basically, what we propose is we can actually using this type of basically the bed material law type of empirically derived entrainment flux for both mud and the sand. So it turns out that this equation actually works okay. So this is what we use in the model. So we use this kind of empirically derived entrainment flux for the mud. So we don't have the erosion all this erosion rate parameter and also the critical shear stress in this formula. But we do have a reference case, as I'm showing here, that uses the classic cohesive theory. So in this classic case, or this is also a reference case, basically we use trial and error to calibrate these two parameters. So yeah, but in this case, in this semi-transform module, we did not consider all those mixed cohesion and and but we do consider the non-cohesive bed. So if the bed is like, for example, sandy bed, that is 30%, like the mud is less than 30% in the bed, then basically we assume, in this classic theory, we assume that the settling, basically there's no, basically we kill the entrainment in the sandy bed. Yeah, basically this is like the classic cohesive sediment transport theory here. But the advantage of introducing this effective flux settling velocity theory is this theory does not require trial and error calibration. So basically, we derive this number based on this number based on the data, rather than we keep changing the settling velocity in the model to match the result. We just derive it from the data, and we plug it into the model, and it turns out that it actually gives okay result. Yeah.
So does it mean, Dongchen, that in case 1 and case 2, we don't have any control on the aerodynamicity of the model?
So yes, no, it's not like you don't have any control. You can still calibrate the settling velocity, of course, but it's like in the case 1, especially in case 1. Okay, in case 1 and case 2, it's like you have a recommended settling velocity that might work already. But in case 3, is in the classic theory, is more like you're shooting in the dark, right? So there's no before you run the model, you don't really know what is the best erosion constant and what is the best critical shear stress, unless you run the model and try, okay, this doesn't work, we need to try and error calibrate. But case 1 and case 2, you have a calculated number there. Then basically you can do micro adjustment of this calculated number. So that's the main difference. So computation-wise, it's relatively cheaper in case 1 and case 2, because you don't need a trend error calibration. Is computation is really intense. Yeah.
All right, Dongchen, are we ready for the hands-on portion?
Okay.
So just real quick, how many people here have MATLAB installed? Okay. Good.
Okay. Yeah. So yeah, basically, do you guys have MATLAB installed in your laptop or desktop?
More than half people, yes.
Yeah.
Not
So
everybody.
yeah, then please go to this link. So this is the again like preprint. So it's still under revision. So this is this is actually code I uploaded last year. So you see the citation here is 23. So you can so you can download the case. Yeah. Then after you download the case, you unzip it. Then you can see these 7 folders in this file. So is that clear? So did you see these 7?
In the instruction file, can you show it? Go to that link to download the files.
Okay. Let me click. Yeah. So sorry. Yeah. So you can see this is the web page, and then you can click here. Or you need to first log in, of course. And then you can click here, download data. Then the data will be downloaded here, down to the default path, whichever. Then you can choose whichever path you prefer. Then basically what you can do, for example, here I already put it here, right? This is a zip file, and this is the unzipped folder. Then you can see if you open this folder, you have all those all these 7 folders, 7 subfolders. So which is shown here. Yeah, let me know if
Sorry, can you
I
put
can.
the link one more time?
Yeah.
Can you show the link one more time?
Maybe you can send it to the chat or show it in the instruction file.
Yeah, can you show us, can you pull up the instruction file or?
Okay. The instruction is this one.
Yes.
Thank you.
Where is the
Okay.
link?
2, 3,
Yeah. There's a link. There's a link in the instruction file. Oh yeah. Maybe I should put the link in the chat. Yeah. Yeah. Oh, actually, it's a second link. Sorry. I think it's a second link.
So the first one was not correct. The second link in the chat.
Yeah. The first one is like the result, basically. The second one is the.
This 2309, is that the ID
Yeah.
number?
The second link is the code. The first one is the result. Yeah.
Another question. Where it has the prerequisite, if we don't have that optimization toolbox, are we not going to be able to run it?
If you don't have the optimization toolbox, will you not be able to run this?
Yeah, the MATLAB needs to have this minimization function.
And does that not come default with MATLAB?
I think it comes default with my MATLAB.
It was
Academic.
in 2023 MATLAB.
Yeah, which
It is
version
by
of
default included in MATLAB 2020?
Most academic licenses have all of the additional toolboxes, and that's part of the optimization.
Do you know, Dongchen, which toolbox this function is belong to?
No, I think it's default. I did not install any external thing. I just installed the. Sorry, I keep changing. I just installed the MATLAB and it comes automatically.
But not all of us have the academic version of MATLAB, and it may not be included in.
I see.
So in that link there, you see the.
Yeah, I put a link here, so it's this is described. I don't know. Also this function is like I don't know which. Do you have most updated MATLAB? So maybe it's added in a later version of MATLAB. So what I'm using is 2019. I think it works. Yeah. Right now, the latest version of MATLAB is 2024. Yeah.
Anyone else confirm they have this function?
I had it in 2020.
Okay.
I have a problem.
Yeah, no, I mean, yeah, you have to buy those extra.
Okay, so not everyone has this function. I think the students, academics do, but not everyone else does.
Okay. So yeah, I don't know. Maybe. Yeah, maybe
will
there are
anything
other.
work, or is it essential for every piece of this model?
So this function is used in the mesh conversion. So basically adapt the ANUGA result to MATLAB like input file. So
Can we deploy bypass that step for people who don't have that function? Can we download the converted mesh?
Yeah, okay.
So that we
So
can continue?
I actually put an example like a processed file here. So it's okay if you don't have this function, you can figure that out later. So I have a
Dropbox, okay.
yeah. I put something in the Dropbox link that people can download. So we can go through
That
that.
is also in the instructions, correct?
Yeah, this is not in the instruction because this link is like for 24 hours. So it will expire in 24 hours.
So what is the link, the Dropbox link in the instructions?
It's not in the instruction, so I can put it in the chat. Yeah. Yeah. So this is the processed result. So using download this file can basically you can skip the optimization function. Yeah.
So what is the link in your instructions under for workshop temporary usage, model inputs, and model results?
Can you repeat the question? I think it's not very.
In your instructions, there is a section that says for workshop temporary usage, and you have two.
Oh yeah.
Yes,
Okay.
that.
I put it here. Okay. Yeah. I
Okay,
forgot.
so we're
Yeah,
not
okay, I
in the
forgot.
chat. Yeah, for
Yeah,
those
so
people in the room that are not in the chat.
So it's the
then
same.
link is-
Yeah. So it's the same. So it's the same link. So it's the same link, but this two link will expire in 24 hours. So, yeah.
Download it fast.
Yeah.
All right, I think we're ready, Dongchen.
Okay. So after you download the code, next thing to do is to download the ANUGA hydrodynamic result. You can download any ANUGA hydrodynamic results from yeah. So here shows the one that I'm using, the one developed by Kyle Wright. I think Antoine also has his result. So basically, you copy this link. I believe this link is also in the like a document. You can see input data. This is basically ANUGA data. So let me put this. Yeah. So you can see this data set is also on the final revision. So it's also a computation result that is under review. So yeah, it's a little bit complicated to first looking at this result. So first thing you need to notice is that this product actually contains three ANUGA hydrodynamic result. Basically the 2016. So you can see this four data corresponding to one model result. So each file corresponding to 1 day of modeling result. So you can see the first three file corresponding to the 2016 modeling result of ANUGA, and then there's this spring 2021 modeling result. That's like around like 14 days ish. Yeah. And then there's a third event that is corresponding to 2021 result. So you can see there are three events here, and then there are some other information in the end. So basically, what this segment module takes is it will take one single event. For example, if you want to model the 2016 event, then you should only download these four files, and then you can yeah, if you then download, here is an example. It's pretty large, so I will not download it right now. So then what you need to do is basically you have this like a empty folder first, hydro input. Basically, what you
can make that bigger for us to see.
bigger.
I don't know if it's possible, but
Okay. Yeah. Okay. Yeah, I don't know how to make the text bigger.
okay, just tell us exactly which folder you're using, so we can't read the words.
Yeah. The first folder, hydro input. So basically, you need to download one event. So here, for example, if you want to run for 2016, then you download these 4 files because these corresponding to 2016. If you want to run spring 2021, then you should download the next like 14 files. You see 2021.
Can you also make the web browser bigger, please?
This.
Bigger. Thank you.
Yeah. So you need to choose one event and download it. So I think the quickest way is to download the 2016 one. It has only 4 files. Then basically you download this file and then you copy paste it into this hydro input.
Can you remind us which website this is, what the data set is called?
Oh, it's in the doc. So this is the this one, the input data.
So it's Kyle's. Okay.
Yeah.
Right now.
You download one event and you put it into this hydro input.
First one. You only need the first one. Okay. So they're just downloading the first 4. Is that correct, Dongchen?
Yeah, you can. Yeah, because first 4 is for 2016. Yeah, that's one simulation. So yeah, maybe I can go here. This 4. Yeah, and other simulations are much longer. So if you want to run other simulation, you can download all of them later. Yeah.
So function, each file is for 1 day, and basically we are simulating for 4 days from.
Yeah, you can. Yeah, you can just run for 1 day.
Okay.
So it doesn't matter. Yeah.
How many
1 day, 2 days.
simulating now?
So I don't think we're going to simulating like any day because it would take a long time.
Okay.
But it's mainly for you to look at what is going on, and then you can run it later at home and make sure. Yeah. Yeah. Let me know you have the file in the folder.
It could take a while.
It's going to take about 2 hours to download this. Yeah, we can keep going.
Or you can choose like a smaller file, but I think it's like this file is 1.1 gigabyte.
Yeah, it's too long.
But we have 25 people downloading it on that internet, so.
Oh yeah, that's
Yeah.
why. Okay.
Okay. So we suggest if you want to follow us around, download that for 1.1 gigabyte, 1.1 gigabyte.
Yeah. Maybe you can download any file that is small. Yeah, not this 4 because these are something else. Yeah, basically any this net CDF file. Yeah.
Okay, go ahead and start, Dongchen. I don't think we're gonna get it downloaded in time.
Okay. Then next step is the pre-processing of this result. So basically, first you put the ANUGA result into the first hydrodynamic input folder. Then you go to pre-processing tools, the folder for pre-processing tools. So what the pre-processing tool does is there are 2 steps. Step 1 is format conversion. So basically, the downloaded ANUGA file is in the format of netcdf. So you should use this load ANUGA nc.m to convert the ANUGA like a result into MATLAB binary, which will generate a .mat file. So here, let me show you an example. So in this folder, I don't know if you can see it clearly. Okay, let me first show the folder here. So in this folder, there are 2 subfolders. You can see 2.1 and 2.2. So first you go to 2.1, and then in this 2.1 folder, there are 4 files. What you're looking for is this load ANUGA nc.m. So in this file, basically, let me I open it here in the MATLAB. So you can see that in this file it requires you to first put the path of the ANUGA file here. Here the default one should be already the hydro input folder. So this program basically will take all the files in this hydro in this hydro this one.
Yeah.
Yeah. So this folder name is already you don't need to change anything. So basically, it will take all the hydrodynamic file in this folder and convert it into MATLAB binary. Then one thing you need to change is the second line here. So the second line, basically you need to tell the program what is the file name you want to save. You want to save the this output of this program. So you can choose your own output here. Then you can just run it. It should work automatically. So So in this process, there are several things being done here. First is the ANUGA result is being converted, of course, into is being read and is being read into MATLAB, and then there are some computation also going on here, especially the Baptist equation for the vegetation frictions is implemented in this code. And using the Baptist vegetation formula, basically this code will generate the Shazy number or the friction like a coefficient for the sediment transport for the full sediment transport module. So you can see the Baptist. There are 4 Baptist parameter read from the ANUGA result. Also, there are some constants that is predetermined in the ANUGA as well. So these constants are I took it from the ANUGA result. So you can change all these constants that is used in the Baptist equation to calculate the friction coefficient. And this shows how the friction coefficient is calculated using Baptist equation. Yeah, that's it. So So you can see you run this case. Basically, you convert the ANUGA result into MATLAB result, and part of the pre-processing is also done in this code. Yeah. So let me know if I can move to the next step.
Does anyone have questions? Has anyone successfully downloaded the file? All right, so people prefer to go on, or people want to try to wait? We only have 20 minutes left with this topic.
Okay. Okay.
Okay, let's keep going.
Okay. Let's keep going. Okay. So this is the first step. The first step, as I said, is using this load anuga.nc.m to convert and do some pre-processing of the ANUGA hydrodynamic result and convert it into MATLAB for like a format. So this node anuga nc.m will generate a .mat file in this folder. You give the name of this .mat file here. So you can see here I generated 3 different like a .mat file here, which corresponds to 3 different like events or 3 different test cases. So this file will be simply put in the same folder of 2.1 here. Okay. Then after this step is done, you can go to the second folder, the 2.2. Basically, the 2.2 is where the optimization function is used. So in 2.2, yeah, it's loading. Okay. So in 2.2 here is the idea of 2.2 is to use this grid and correct hydro.m to convert the unstructured mesh in the ANUGA into the Cartesian mesh. So in MATLAB, the mesh basically looks like this. Use a Cartesian mesh in this semi-trans module. So convert the ANUGA unstructured mesh and map the hydrodynamic result onto the like a MATLAB Cartesian mesh. So this is the second step. In this process, this optimization function is used to do the conversion and do the mapping. So the second step, you can see here, the second step, the file looks like this basically. So it will first you need to load the file that you generated from step 2.1. So you can put your file name here, like previously. Then this like a converted mesh will be generated in this folder, name, basically into the third folder of model input. Also, you need to determine the file name here. So I simply put you should change all these. Basically, you change all these file names. And you look at the location of the files and change file names. Basically, you see you take the .mat file from step 2.1 and convert it into the model input, and then put it into the folder 3 model input. And here you specify the name here.
Can we choose any grid size we want, or our grid size should be based on the ANUGA?
Yeah. So you can choose the grid size in this process. So this is the process that generates the MATLAB, like the semi-transform grid in MATLAB. So you can choose the grid size. So I'm putting a 100 here. You can put a smaller or larger grid size. Grid size depends on your needs. Yeah, so you can change. So the smaller grid size will generate a bigger mesh and will slow down the process. Okay, so this is grid size. There's a second thing you need to specify in this case is to determine what is the modeling domain. So here, basically, it's sort of a little bit of hard code in this code. So basically, you need to put the x and the y coordinate into. You need to tell the program what is your sediment transfer modeling domain of your sediment transfer model. For example, here in this example case. Basically, I'm telling the program that so basically I'm telling the program that I'm going to model this shaded region. So then I need to give the x1 also so x1, y1, x2, y2 here. So basically I need to give this what is basically I need to determine this box. So this box is determined here, basically the y limit and x limit. Yeah, you can play with this later, of course. Yeah, but right now it's okay to leave it by default. And then it's the optimization function that maps the mesh onto each other. Yeah, so you can see the rest of them is in the loop of mapping. Yeah, so here the key is you determine the file names, of course, and then you determine the grid size. You determine what is your modeling domain. Yeah, so let me know if you want to move on to next step.
Ready to move on to the next step?
Okay.
Okay, go ahead.
Okay, so this is basically the pre-processing you need to convert the ANUGA into MATLAB input. So first load ANUGA nc.m. Second is map the mapped unstructured mesh into Cartesian mesh using the grid and the correct hydro.m. Okay, then after these two steps, as you can see here, it will generate a MATLAB .mat file into the folder 3 model inputs. Okay, so now we can go to 3 model inputs. So you can see there are again several .mat file I generated here using different event to model different events. So this file should be automatically generated here. Then let me show next step. Okay, so in this folder, basically, you should already have the. So in this sediment transfer model, you need 3 inputs. The first input is the bed grain size distribution or the fraction of mud in the bed in the modeling domain. So here, this file is in the format of txt. So it is basically XYZ file. This should come automatically already in the folder. So if I go into the folder, model input, you see this bed composition, grain size distribution interp is here. So you can open it. It's a txt file. You can take a look at what's inside.
Can you explain where did you get that bed composition file? From the
Yeah,
Sediment,
yeah, yeah. It should already in the folder. Yeah.
Where did you get those information? the bed size composition.
This one.
Yes.
Can you
What's the
repeat the
source of
question?
that?
Oh, the source of this. Okay. So I generated this bed grain size distribution using the DirtX data collected in the channel. Also, this part of data front I use John Shaw's data, but it's not published, so I didn't put the data here. I just put the interpolated map here. Yeah. So this part is generated using John Shaw's data, and this part is DirtX data. You can download it from DirtX website, from the deck. Yeah. So yeah, so this is how the map looks like, and this is the format of this file is basically X, Y, and Z. So this Z is the fraction of mud in the bed. So you can see there's more mud in the further part of the basically in the ocean, and it's more like a coarse bed, sandy bed in the channel. And I assume there's a constant mud fraction of around 0.6 on all this wetland. So that's the assumption made in this. But you can, I mean, this is just an example file, so you can generate your own grain size distribution or the fraction of mud file. Yeah, following this format. So this is the first input file. The second input file is the .mat file that is generated using previous previous pre-processing tools. Okay, I'm not expecting you can generate this file today, so I put the link here. You should be able to go to this link and download this file. So let me try it from my side to see if I can download this myself. So you go to this model input and into the folder 3 model input. Yeah, let me wait until download finish. And then you see the file is here. Then I copy paste it into this model input, 3 model input. Okay. So then this is the second model input, and then there's a third model input. Is the boundary condition. So you need to specify the time series of the boundary condition of the, for example, the inflow sediment concentration. Also, so this is basically what we need to do here is you can go in, you can just go into one example file here. So in this boundary condition, basically you have several columns. One is a time. It doesn't matter the order, but you need to say this column is time. So basically it counts in second. It starts from 0 second all the way to the length of the simulation. And then you need to specify what is the sand concentration and what is the mud concentration. So yeah, I mean, all these are flexible. So you can, it's an open source code. You can change it later if you want to use it. You can even add more classes. So here I'm only have mud and sand. You can have silt and maybe more classes for sand, etc. So
we have 5 more minutes.
Yeah. What's the question?
We have 5 more minutes. Maybe move on quickly to the next step.
Okay. Okay. Yeah. Okay. So yeah, this is basically the three input file that you need to run the model. The bed grain size distribution in the form of TXT file, the hydrodynamic result .mat file, that is generated using all these second step pre-processing tools. And then the boundary condition file, this is a comma separated variable file as time series. So after this, you can go to next step. Finally, you can start to run the model. You go to the folder for model code, and you find you will see there are several files in this folder. So you find the other files, they are all functions. So you locate this main model file here. So if you come here, let me model code. So you find this main the main file of this model. You open it. It's a long file. So basically, all the parameters you need to determine is at the beginning of this file. So you can explore all these parameters later, or you can ask me if you have any questions later. Send me a message. So you can see here you need to specify what is your input file. First the .mat file, then the time series file .csv, then the bed composition file, the grain size distribution file, the fraction format .txt file. Then you need to specify that which folder you want to save the result. So you can save the result to any folder you want to save it, and then you want to specify a prefix of your modeling results. You can put any prefix of your modeling result here. And then, yeah, there are many sediment transport parameters you can play with here. Here I only mention one thing, is this morphological factor vector. So this morphological factor will determine how many cycles you will run the model. So the model is designed in a way that basically it will repeat to run one event and adjust the bed grain size distribution. So each time, because the morphodynamic model is a slow process, so by repeating running the sediment transform model, the bed grain size will keep adjusting. And here, the length of this vector will determine how many repetition you want to make in this process. So here I put 5, the length of 5, then there will be 5 repetition of this simulation. And the last round of simulation will be taken as the modeling result. So the modeling result basically looks will be the modeling result will be in the folder. Let me see. In the folder 5 model result. So it will look like the model result will look like something like this. So basically, you can see that it has a prefix of the model result. Then it follows by the which repetition. So for example, this is a repetition 1. It will break into it breaks the result into pieces. So this is, for example, repetition 1. And the third file of the first repetition. And what you are looking for is, because all this file is like the first 4, because I set the repetition time of 5. So the first 4 repetition result will be like the hot start, and then the last round of this simulation will be taken as the should be considered as the final result. So you should go to repetition 5, and you see this repetition 5 has 31 files. So this is basically how the result file look like. So I uploaded one example result file here. So yeah, so let me show you the. It should be in the doc. So this is one example of the modeling result. And then if you can download this result and put it into the folder, into the folder 5, the model result folder, then you can start to use post-processing tool to process the result and generate all these final like result images. So here I'm just because of time, I will just show quickly one comparison between the modeled suspended sediment concentration and the average NG derived total suspended sediment concentration. So here you can see in this file there's a in this folder there's a file called compare average 2021 0402.m. So in this file you can see you first put the result name, file name here, and then this is basically the interpolated average NG result that I generated myself. You can and then basically I mapped the average NG result on top of the MATLAB like a Cartesian grid. Then there's you can go to look at the details of these post-processing files. There are several files offered. So let me quickly run this file, and then it should generate the same file. Okay, so this is the April. This is April 2nd file. So let me generate this April 1st. Yeah, so you should generate something like this. So this is basically the difference map between the average NG total suspended sediment and the total suspended sediment concentration calculated in this module. Yeah, so that's all. That's all I have.
Thank you.
Yeah.
Any questions in the room? So is this all of the material you wanted to cover today?
Yeah, that's all the material I want to cover today. Yeah.
Did anyone successfully download the file?
Yeah, so there's a question asked the Delft 3D. Yeah, that's a good question. So yes, so Delft 3D model can be used to simulate the effect of sediment accretion in this domain, of course. So actually myself, I'm using OpenDynamic to model the land accretion at the Wax Lake. So again, this model is developed by previous effort by Gerard Saute. So I was just complete his mission. So second thing is Delft 3D uses its own sediment transport theory. So that is different from the sediment transport theory that is implemented into this sediment transport module. So the main difference between this one and the Delft 3D is the theory implementation. So yeah, of course you can also personalize the theory by modify the source code of Delft 3D, but I was told that is a tough job. Yeah, so for myself, for my continuation in the DataX project is like I use OpenDynamic, which is open source code, that to implement the exact same theory as implemented into this Delft 3D, as implemented this DataX sediment transfer module to model the morphodynamics. Yes, so the main difference is what the theory is. That's the main difference. Yeah.
All right, thank you so much.
Yeah.
Thank you, Dongchen.
Thanks. Yeah, thanks.
All right, so we have a 13-minute break now. So we start again at 3:15 with the NUMAR model, which is the eco-geomorphic model, looking at the plant contribution to soil elevation. And Pranita is here in the back, so we will be teaching us how to use the model. So 3:15. Thank you.